Imagine waking up one morning and realizing the sun, the same star that gives life to Earth, has just fired a storm so powerful it could shut down satellites, cripple global communication, and plunge entire continents into darkness. This isn't science fiction. It has happened before, and it will happen again. Right now, invisible forces from the sun are constantly slamming into our planet at millions of kilometers per hour. And the only thing standing between modern civilization and total technological collapse is something you never see, never feel, and almost never think about: Earth's magnetic shield. But how strong is it really? And what does it endure every single day to keep us alive? In this video, you will discover what solar storms truly are and how they form deep within the sun's violent surface, how streams of charged particles travel across space and collide with Earth, what the magnetosphere actually does when a solar storm hits, and why this invisible shield bends, stretches, and sometimes nearly breaks under the pressure. You'll also learn about the most dangerous solar storms in human history, what would happen if a Carrington-level event struck today, and whether Earth's magnetic field is weakening at the worst possible time. Welcome to Where the Light Ends, a place where space grows silent, light fades, and the universe begins to reveal its darkest secrets. To understand what Earth's magnetic shield endures, we first have to face the source of the threat itself. The sun is not a calm, steady ball of light hanging peacefully in space. It is a massive, unstable nuclear reactor, constantly boiling, twisting, and tearing itself apart under forces almost impossible to imagine. Every second, deep within its core, hydrogen atoms fuse into helium, releasing staggering amounts of energy. This energy fights its way outward for thousands of years before finally exploding into space as light, heat, and radiation. But sometimes the sun releases something far more dangerous than warmth. Solar storms are born when the sun's magnetic field becomes unstable. The sun is threaded with colossal magnetic loops, some stretching hundreds of thousands of kilometers above its surface. These magnetic fields are constantly moving, twisting, and tangling as the sun rotates faster at its equator than at its poles. Over time, stress builds, and when that stress becomes too great, the magnetic field snaps and reconnects in an event known as magnetic reconnection. When this happens, energy that has been trapped for days or weeks is released in minutes. The first sign of a solar storm is often a solar flare. A solar flare is a sudden, intense burst of radiation that travels at the speed of light. Within 8 minutes, that radiation reaches Earth, capable of disrupting radio signals, GPS systems, and satellite electronics. But solar flares are only the warning shot. The real danger often follows behind. In many cases, solar flares are accompanied by coronal mass ejections, colossal clouds of charged particles ripped straight from the sun's outer atmosphere. These clouds can weigh billions of tons and travel through space at speeds exceeding 2,000 kilometers per second. Unlike light, these particles take 1 to 3 days to reach Earth. During that time, they expand, evolve, and sometimes grow even more dangerous. What makes coronal mass ejections so destructive is not just their speed, but their magnetic structure. These clouds carry their own magnetic fields, and when they collide with Earth's magnetic field, the interaction can be violent. If the magnetic orientation of the incoming storm aligns in just the wrong way, Earth's defenses are forced open rather than deflecting the impact. This is where the story becomes personal, because modern civilization is uniquely vulnerable to solar storms. For most of human history, a powerful solar storm would have gone largely unnoticed. The skies might glow with auroras far from the poles, compasses might behave strangely, but life would go on. Today, that is no longer true. Our world is wrapped in a fragile shell of technology. Thousands of satellites orbit Earth, enabling communication, navigation, weather forecasting, and global finance. Power grids stretch across continents, delicately balanced to deliver electricity with precise timing. Fiber optic cables and radio networks pulse with data every second. All of it depends on stable electromagnetic conditions, and solar storms are capable of ripping those conditions apart. When a coronal mass ejection strikes Earth, it compresses the planet's magnetic field on the day side and stretches it into a long tail on the night side. This sudden deformation generates powerful electrical currents both in space and on the ground. In space, satellites can be exposed to intense radiation that damages electronics, degrades solar panels, and shortens operational lifespans. In Earth's atmosphere, increased radiation can interfere with high-frequency radio communication, especially over polar regions. On the ground, the danger becomes even more serious. The fluctuating magnetic field induces electric currents in long conductors, power lines, pipelines, and undersea cables. These geomagnetically induced currents can overload transformers, cause widespread blackouts, and permanently damage critical infrastructure. Unlike many other disasters, this damage cannot always be repaired quickly. Large transformers can take months or even years to replace. This is not a hypothetical scenario. In 1859, the most powerful solar storm ever recorded struck Earth. Known as the Carrington Event, it caused telegraph systems around the world to fail spectacularly. Some telegraph operators received electric shocks. Others found that their equipment continued to transmit messages even after being disconnected from power sources. Auroras were seen as far south as the Caribbean, lighting up the night sky in blood-red hues. If an event of similar magnitude were to occur today, the consequences would be catastrophic. Studies suggest that a Carrington-level storm could cause trillions of dollars in damage and leave millions without power for extended periods. Satellites could be lost permanently, GPS could fail, financial systems could freeze, and recovery could take far longer than most governments are prepared for. Yet despite this danger, solar storms are not rare. The sun follows an approximately 11-year cycle of activity, swinging between periods of calm and extreme volatility. During solar maximum, sunspots multiply, solar flares become more frequent, and coronal mass ejections erupt with alarming regularity. We are not safe simply because nothing disastrous has happened recently. In cosmic terms, recent history means almost nothing. Even smaller storms can have real consequences. In 1989, a geomagnetic storm caused by a coronal mass ejection collapsed the power grid in Quebec, plunging millions into darkness for 9 hours. Satellites malfunctioned. Radio communication was disrupted, and that storm was far weaker than the Carrington Event. What makes this threat especially unsettling is how little control we have. We can observe the sun. We can detect solar flares and track coronal mass ejections as they race toward Earth. We can issue warnings and, in some cases, temporarily shut down vulnerable systems. But we cannot stop the storm. All we can do is hope that Earth's magnetic shield holds. And that brings us to the heart of the mystery. Earth's magnetosphere is not a solid wall. It is a dynamic, constantly shifting structure shaped by invisible forces. It stretches tens of thousands of kilometers into space, forming a protective bubble that deflects most solar particles away from the planet. Without it, Earth would look far more like Mars, a barren world stripped of its atmosphere by solar wind. But Earth's magnetic field is not invincible. It weakens, strengthens, and even reverses over geological time. Scientists have discovered that it has been slowly weakening over the past 2 centuries. In some regions, such as the South Atlantic anomaly, the magnetic field is already unusually weak, exposing satellites to higher radiation levels. So the question is no longer whether solar storms are dangerous. We already know they are. The real question is how long Earth's magnetic shield can continue to protect a civilization that depends so completely on fragile technology, and whether we truly understand what it endures when the sun decides to unleash its fury. Because every solar storm that slams into Earth is a test of physics, a test of infrastructure, and perhaps most of all, a test of how prepared we really are for a universe that does not care about our plans. To understand how Earth survives solar storms, we have to look at something that cannot be seen with the eye, photographed by a camera, or touched by hand. Earth's magnetic field is an invisible force generated deep beneath our feet, far below oceans, mountains, and cities. It begins in the planet's core, where temperatures rival the surface of the sun and pressures crush matter into exotic states. At Earth's center lies a solid inner core made primarily of iron, surrounded by a molten outer core that flows slowly over geological time. As this electrically conductive liquid iron moves, it generates powerful electric currents. Those currents create a magnetic field, and that field extends far out into space. This is the geodynamo, a natural engine that has been running for billions of years. Without it, Earth would not be the planet we know today. The magnetic field does more than guide compasses. It shapes a vast region around Earth called the magnetosphere, a protective bubble carved into the solar wind. On the side facing the sun, this bubble is compressed by the constant stream of charged particles. On the night side, it stretches into a long magnetic tail that extends hundreds of thousands of kilometers into space. When the solar wind is calm, Earth's magnetosphere quietly does its job. Charged particles are deflected around the planet, sliding along magnetic field lines and flowing past harmlessly. Some particles are trapped, forming radiation belts that encircle Earth. Others are guided toward the poles where they collide with atmospheric gases and produce the auroras, shimmering curtains of green, red, and purple light that dance across polar skies. Under normal conditions, this interaction is beautiful and benign. But during a solar storm, everything changes. When a coronal mass ejection slams into Earth, the magnetosphere absorbs the impact like a shield taking a blow. The dayside boundary of the magnetosphere can be pushed dramatically closer to the planet, sometimes compressing to less than half its usual distance. At the same time, the nightside magnetic tail stretches and stores enormous amounts of energy. This process loads the magnetosphere with tension, much like pulling back a bowstring. Eventually, that energy must be released. Deep within the magnetotail, magnetic reconnection occurs again, this time not on the sun, but in Earth's own magnetic environment. Field lines snap and reconnect, flinging charged particles back toward the planet at incredible speeds. These particles spiral down magnetic field lines and slam into the upper atmosphere, triggering intense auroral storms. During powerful events, auroras can be seen thousands of kilometers from the poles, glowing over regions that almost never experience them. But the spectacle comes with a price. As the magnetosphere reconfigures itself, powerful electrical currents surge through near-Earth space. These currents, known as geomagnetic storms, distort Earth's magnetic field at ground level. And whenever a magnetic field changes rapidly, it induces electric currents in conductors below. This is basic physics, and it is the mechanism that turns space weather into a terrestrial disaster. Power grids are especially vulnerable. High-voltage transmission lines span vast distances, making them perfect antennas for geomagnetically induced currents. When these currents enter transformers, they can cause overheating, voltage instability, and permanent damage. In extreme cases, protective systems shut down entire sections of the grid to prevent destruction, leading to massive blackouts. Satellites face a different kind of danger. During solar storms, Earth's upper atmosphere heats up and expands. This increase in atmospheric density creates additional drag on satellites in low Earth orbit, causing them to lose altitude. Without corrective maneuvers, some satellites can re-enter the atmosphere prematurely and burn up. At the same time, energetic particles can penetrate satellite shielding, flipping bits in memory, damaging sensors, and degrading solar panels. Even astronauts are at risk. Outside the protection of Earth's atmosphere and magnetic field, radiation levels during a major solar storm can be lethal. This is why missions to the Moon, Mars, or deep space must carefully monitor solar activity and plan for emergency shelter during solar events. Earth's magnetic shield is not just protecting technology, it is protecting life itself. Yet this shield is not uniform. Earth's magnetic field varies in strength across the planet, and in some regions it is significantly weaker. The most famous of these regions is the South Atlantic Anomaly, an area stretching over parts of South America and the South Atlantic Ocean. Here, the inner radiation belt dips unusually close to Earth's surface. Satellites passing through this region are exposed to higher levels of radiation, and many instruments are powered down temporarily to avoid damage. The existence of such weak spots raises an unsettling question. What happens when a solar storm targets Earth at its most vulnerable points? Adding to this concern is the fact that Earth's magnetic field is not constant over time. Measurements show that it has weakened by roughly 10% over the past 2 centuries. Magnetic north is drifting rapidly across the Arctic, moving faster now than at any time in recorded history. These changes are part of natural processes, but their timing is uncomfortable. We are entering an era of unprecedented technological dependence, just as our planetary shield shows signs of instability. On geological timescales, Earth's magnetic field has flipped many times. During these magnetic reversals, the field weakens significantly before re-establishing itself with opposite polarity. There is no evidence that a reversal causes mass extinctions, but modern civilization has never experienced one. If a major solar storm were to strike during a period of reduced magnetic strength, the consequences could be far more severe than anything we have faced before. Despite all this, Earth's magnetosphere remains remarkably resilient. It flexes, absorbs, and redirects energy on a colossal scale, protecting the planet day after day. Every solar storm that reaches Earth is a reminder of just how hostile space truly is, and how extraordinary it is that life has survived here for so long. But resilience does not mean invulnerability. The magnetosphere is constantly under attack, constantly adapting, constantly enduring. It is not a static barrier, but a living system shaped by forces both inside and outside the planet. And as solar activity intensifies, the stress on this system increases. Understanding how Earth's magnetic shield responds to extreme events is no longer an abstract scientific question. It is a matter of global security. Because when the next great solar storm arrives, and it will, the true test will not be whether the sun unleashes its power, but whether our invisible shield and our fragile civilization beneath it are ready to endure the impact. For most of human history, Earth's magnetic shield did its work silently. It bent the solar wind, absorbed cosmic violence, and allowed life to evolve without ever demanding attention. But the modern world has changed the stakes. Today, a single extreme solar storm has the potential to disrupt not just technology, but the foundation of global civilization. To understand the future, we must confront a difficult question. What happens if Earth's magnetic shield is pushed beyond its limits? The greatest danger does not come from an average solar storm, but from a rare extreme event. These storms occur when massive coronal mass ejections strike Earth head-on with a strong and sustained magnetic orientation that directly opposes Earth's field. In such cases, the magnetosphere is forced open for extended periods, allowing solar energy to pour inside far more efficiently than usual. The longer this coupling lasts, the more energy is transferred into Earth's magnetic system. If a Carrington-level storm were to hit today, the effects would unfold rapidly. Within minutes, intense radiation from solar flares would disrupt high-frequency radio communication, affecting aviation, maritime operations, and emergency services. GPS signals could become unreliable, causing navigation errors across air, sea, and land. Satellites would begin experiencing electronic anomalies almost immediately. Within hours, geomagnetic disturbances would propagate through Earth's magnetic field. Power grids in high-latitude regions would be the first to feel the impact. Transformers would be exposed to geomagnetically induced currents far beyond their design limits. Some would overheat and fail permanently. Protective shutdowns could cascade across interconnected grids, triggering widespread blackouts that spread far from the storm's initial impact zone. What makes this scenario especially dangerous is the time scale of recovery. Large power transformers are custom-built, expensive, and difficult to replace. Manufacturing and transporting them can take months or even years. During that time, affected regions could remain without stable electricity, disrupting water supply, healthcare, food distribution, and communication. In a world where almost every system depends on power, prolonged outages could quickly become humanitarian crises. Space infrastructure would also suffer. Some satellites would be lost entirely, either through radiation damage or orbital decay caused by atmospheric expansion. Others might survive, but with degraded performance. The loss of weather satellites alone would severely impair storm forecasting, agriculture planning, and disaster response. Communication satellites could fail, isolating regions and disrupting global trade and finance. The economic consequences would be staggering. Modern financial systems rely on precise timing signals provided by satellites. Even small disruptions can cause errors in transactions and data synchronization. A large-scale failure could freeze markets, interrupt supply chains, and cause losses measured not in billions, but in trillions of dollars. Unlike many natural disasters, the damage would not be localized. It would be global. Yet, as alarming as this sounds, the greatest vulnerability may not be technological, but psychological. Solar storms are invisible. They arrive silently, without earthquakes, without winds, without flames. This makes them easy to ignore and difficult to prepare for. Governments tend to prioritize threats that are immediate and tangible. Space weather does not fit neatly into that category, even though its potential impact rivals the most severe natural disasters. Scientists are not powerless, however. Over the past decades, our ability to monitor the sun has improved dramatically. Spacecraft constantly observe solar activity, watching for flares and coronal mass ejections. When a dangerous event is detected, warnings can be issued hours or even days in advance. Power grid operators can temporarily reduce load or disconnect vulnerable components. Satellites can be placed into safe modes. Astronauts can seek shelter. But warning does not equal protection. Even with perfect forecasting, there are limits to what preparation can achieve. Some systems cannot be shut down without severe consequences. Others are simply too old or too interconnected to adapt quickly. Much of the world's infrastructure was built without space weather in mind. It was designed for efficiency, not resilience against cosmic events. Looking further ahead, scientists are exploring ways to harden our civilization against solar storms. New transformer designs aim to resist geomagnetically induced currents. Satellite electronics are being built with greater radiation tolerance. Power grids are being studied to identify weak points and develop rapid response strategies. In space exploration, future missions may include dedicated radiation shelters and advanced forecasting tools. There is also a deeper, more unsettling consideration. Earth's magnetic field will not remain constant forever. It will continue to evolve, weaken, and eventually reverse again. While this process unfolds over thousands of years, it reminds us that our planetary shield is not guaranteed. Civilization, by contrast, has existed for only a few thousand years, a brief moment in geological time. This realization forces a shift in perspective. Solar storms are not anomalies. They are a fundamental part of our star's behavior. Earth's magnetic shield has endured them for billions of years, shaping the conditions that allowed life to emerge. But modern civilization has placed itself in a uniquely fragile position, balanced delicately atop systems that assume a stable space environment. In the end, surviving solar storms is not just about physics or engineering, it is about humility. It is about recognizing that our planet lives in a dynamic, sometimes hostile universe, and that our greatest defenses are often invisible. Earth's magnetic shield is one of the most extraordinary natural systems we know. A silent guardian that bends cosmic violence away from our world. But it is not infinite, it is not unbreakable, and it will continue to be tested. The next great solar storm may arrive tomorrow or centuries from now. When it does, the outcome will depend on how well we understand the forces at work, how wisely we prepare, and how seriously we take a threat that arrives not with sound or fury, but with silence. What unsettles me most about solar storms is not their power, but how quietly they threaten everything we've built. There are no explosions, no warnings in the sky, just invisible forces capable of silencing our world in hours. We like to believe that technology makes us untouchable. Yet one violent moment from the sun could remind us how fragile modern life really is. Earth's magnetic shield feels like something we can take for granted, but in reality, it is a constant struggle happening far above our heads. Every satellite, every signal, every system we rely on survives because that invisible barrier holds. And the more we understand it, the more I realize that surviving the future may depend less on controlling nature and more on respecting how close we already are to its limits. This is where the light ends. Thank you for watching. And remember, some questions are meant to remain unanswered.